we'll start talking. So, I think first things first, let's just talk about a couple things. So, we have an exam date now for the second exam. So, exam 2 is going to be in 2 weeks from now. Exactly 2 weeks from now, on Monday. It's on November 16th. And we have November 11th off, I think. So, the review is going to be next Monday, and then we're going to have about a week in between, and then we'll be having the actual exam. And it's going to cover everything up to linked lists. So I believe that would be the not inheritance. What is it? What I'm looking for? So abstract and virtual classes and functions up to today, I guess, which would be linked lists. So that'll include everything on the syllabus, recursion, operator overloading, templates, and exception handling. I think that's about everything. I mean, we can double check the syllabus, I guess. So yeah, we'll cover everything from here. So this wasn't on the last exam. The abstract classes and virtual functions, operator overloading, exception handling, the templates and the generic types. Polymorphism is, I guess, something we've technically been doing the whole time. I'm not really sure where that's on there. Recursion stuff, and then linked list will be the last thing. So everything else here afterwards will be on the final, which I mean kind of has to be comprehensive for a class like this, because you kind of need to know how to program to be able to answer a lot of the questions anyways, which relies on the other stuff. So there's that. We do have Veterans Day on the 11th, so we have off the Wednesday that it comes before the actual exam. So just consider, I guess, if you need time to ask questions over that weekend, we have that whole long period. But I'm going to do the review a week in advance. As a result, because I know that this is the case, I've kind of tried to spread the assignments out, because I don't think we're going to be having one due on the week of the exam again like the last one. But I haven't spread it out too far yet, just in case. So I'm going to wait and see what the other instructors say, and then we'll take it from there. But I don't think assignment 8 is all that long, anyways. At least just from when I was looking at it. So I don't really think that one will take too long. And assignment 9, I wrote, and I know that one might take a while just conceptually, but it's not very long from a code perspective. It's maybe about 100 lines of code. Right, so there's that. I extended assignment 7 to just before class on Wednesday, and I wanted to make sure it was due before class so that we could go over the write-up. So there's that. Right, so I think that's all we had to talk about that was related to that sort of stuff. So let's take another look at linked lists really quick. Right, so what is the review? It will be on... So if we have the 11th off, then that would be the 9th. So we'll do a review on the 9th. So exactly a week from today. Right, so the thing we were talking about last time was the idea of like a linked list, which was a list that wasn't strictly like next to each other in memory, kind of like how an array is always all these memory cells right next to each other in memory, but we kind of wanted to create one where it maybe pointed to other spaces in memory, and they were kind of separate. So what we had was something like this, right, where it was a bunch of these nodes. And in the nodes, we had two fields. So one was the data field, which held the actual data, so similar to the actual memory cell of an array. And then we just had a pointer to another node. So we had some sort of structure like this, and it would have kept going until we hit the end. So it would maybe do this, and then for the sake of my drawing, maybe I make it go down sometimes just to fit some room. And then at the end of the list, what we had was null, right? Which marked that we were at the end of the list. So if we don't point to anywhere, then we could, end. And that's fine. And so we talked last time about the three basic operations that a data structure like this has, which would be insert. So we have insertion, we have deletion, so removing something from this list, and then we had a lookup or search. And so these are the three operations, I would say, of most data structures. So a lot of data structures you'll learn if you take 302 have this have these three things, and you'll see that it happens a lot across a number of different data structures, and you might even see some more if you take some 400 level classes. That we have some other data structures, and generally they have these three things to them. So we need to be able to put something in it, remove something from it, and then we have a lookup part. Right. So with the structure we had, when we went to go insert, just to refresh, there we go. What we had was, if we wanted to insert something at the end of the list, then remember we always had a pointer to the starting point of the list, which was called the head. So we had a head pointer, and then we would, if we wanted to insert something, what we would do is we would traverse the list until we got to the end. So we'd say, let's start at the head, and then we'll follow this pointer here to the next one until we find out that there's nothing at the end anymore, and then we'll take a new node and we'll change this pointer to point to it instead, is what we said. So that was the idea of our insert. And then our delete, we said if we had something like this, then if we wanted to, let's just say, delete this one, then what we did was we had to keep a pointer not only to this one, but also to the one before it. That way, when we delete it, we know that we can take this pointer, wrap it around so that it points to this one, and then we sever this one in the middle. Right, so that's what we did. And then actually one thing I don't remember if I talked about was if we went and we had to delete the head, then we have to do something extra. Or I guess if we kept a tail pointer, I guess was something that we said hypothetically, we might have to do something special as well. Which is, if I was to delete the head, then consider that I do have this head pointer here, right? So if I need to delete this, what I'll need to do is set the head to point to the next thing, because I'm going to remove the current head, and then sever that link. And I've written code for this, so we can take a look at it in a moment. But that was the idea of a delete, is that we redirect the pointer around it before we remove it. Otherwise, this data, right, if I was to just delete this thing first, then this pointer, this black pointer that was there originally, it would have pointed to data that's gone, and we would have gotten a bad read access error. So we need to move the pointer around the node that we're removing before we delete it, was the idea. And then the last operation we had was lookup, which was basically just the same. I don't think I'll even draw that one out. It was the same as insert, but we just stopped at some point. So we would hop along and traverse the list basically until we hit the exact place that we want. So I wanted to take maybe a quick look at the code for that, and then talk about a different approach, and then maybe how we can actually use something like this to some sort of practical usage. Right, so I've written some code here. This is the main body. It's not too important. It just inserts some things into the list, prints it, and then deletes it and prints it again to show that the thing has been deleted. And then for the sake of the example, because I know you're doing the exceptions assignment soon, I've written a example of exception handling. So I have a try here where it tries to delete something at the 20th index, but there are only 4 things in the list, so it's going to fail on that. And I've written an exception class that just gets thrown here. So that way you have it for reference, I guess. So we have a couple things. We have that out of bounds exception class, which is just the normal exception, and that's just if we try to access something that's not there, it'll just throw that so that we can specify that. So I've gone ahead and I made this a template class as well. Again, maybe for practice, but also because it's a little practical here. So we have a node that can hold any type of data. So it holds, again, we've been saying that the node holds some data, which is what it actually stores, and then it keeps a pointer to the next object in the list so that we can actually do the traversal of the list. And excuse me, and what we said was that whenever we create a new one, that the way we should do it is we should put some data in it and we should make the next pointer be null if we're going to throw it at the end, because the end always had a pointer that was null, and that's kind of how we told that it was at the end of the list. And we could definitely set it to be something else. We could set it to point back to the head if we wanted to. In that case, it would be circular. But yeah, I think the default way that we should handle this is setting it equal to null. And so what we had in the length list was we had the head pointer, which pointed to where the head was, and then we wanted to do an insert, delete, a lookup, and then I just wrote one that prints for the sake of the example. And then we have a constructor. So the insert here, like we were saying, if the head is null, so in other words, if the list is empty, then we just throw the node at the head. Otherwise, we need to go through the list, so we keep some sort of node that keeps track of where we are in the list itself. So it starts at the head, and then it will set itself equal to the next node, so it will follow this pointer to the next one, and it will keep doing that until it sees that the pointer is null, which tells it that it's at the end, in which case we can insert the next node at the position. Right, so this one just traverses until it hits the end, and then this throws it at that node, which is the end. And then we said for the delete and the insert last class that one way we could do it is we could just follow that many nodes in order to actually get somewhere. So this one would be like index 0, index 1, and index 2, right? So if I was to keep like a traditional array, this would be 0, 1, 2, and this new one would be 3. And so if I was to access the element at axis 0, I would have to follow the pointer 0 times from the head. And to get to this one, I'd have to follow the pointer 1 time from the head, 2 times from the head, and 3 times from the head. So what this code does here is it says follow it for the amount of times that was asked, so the index. In that case, keep following it like we had there, so the current node will equal the next. And then we said we needed to keep a previous for that reason we said earlier for the deletion, where I need to redirect this pointer around it, so I keep a reference to the previous here so that we can do the actual deletion down here. And so we have the two cases, one where it's the head, so we need to reassign the head to be the new one, and then the other one which will take the previous node, the next of it, and set it equal to the one that we're deleting next. So that would do this part here. So it's going to take the previous pointer and set it to this one's pointer. So this ends up pointing over to here instead of to the one that we're deleting. That's what we wanted to do. And then we just delete the current node and get rid of it. And then the lookup is basically the same. So it goes through the list, and it will go index many times until it gets it. And then here I just have it return the data. So we'll return whatever is at that node that it's storing. And then the other thing I have here is that we have a out of bounds exception. So if we get that we're about to hit a current node where it is null, in other words, we're about to follow that link that is null at the very end of an array, or sorry, a linked list, then we know we don't have any more data to actually go through, so we're about to go out of bounds of that, of that linked list. So I just have it throw an exception here, and then I catch it in main. So here I expect it to go out of bounds, so I say catch that out of bounds exception. And so again, that will just make it so that the program doesn't actually crash. Right, so I'll let you run this on your own. It does work, I've tested it, and I'd like to add to it in a little bit. So that was just a brief refresher from last class. Does anybody have any questions on any part of the linked list so far? Because we're going to talk about it a little bit more, but it's we're going to kind of expand upon it. So if you have any questions, please let me know. So let's maybe do these in a different way. What I wanted to do is propose a different way to do the insertion, deletion, and lookup that instead of using while loops uses recursion. So maybe we can do a recursive insert, a recursive deletion, and a recursive search lookup. I think the first thing we'll do is the recursive insertion. So let's make a recursive linked list, which again will basically just have access to the same thing. So it will still have a head pointer and some nodes, and that's really it. So we'll say here we have some sort of head pointer, and it points to more nodes, point to more nodes, and we'll just say this one's the last one. So I have a head here pointing to the beginning, and then I want to insert some sort of new node. So our idea was that we want to traverse these, right, and get it to the end. Now, something I want to consider is when I follow this here, then really I can't go backwards, right? So if I was to get to the point where I start at the head and I was saying, oh, let's go to the next one, then I'm only allowed at this point, the rest of my traversal is only going to have to do with this part of the list, right? This red part here. Now, if I was to ignore this head altogether, is there anything that you notice about what's left over? Does it look similar in any way? And so what I guess I would say is it kind of does, because this here, if I do just this red part, is another linked list. Of size 2. So whereas the first one was a linked list of size 3, the whole thing I have, then this part right here, just these two nodes, and the pointer that I'm following to it, is also a linked list, and it's a linked list that's one smaller. It has the head chopped off. You could say the body, I guess, then. The body of the linked list is also a linked list. And that's good because that's kind of the way recursion works, right? Is that we operate on something that is basically like a smaller case, right? So maybe one way I could think about this insert is recursively, if I had a insert here and it just had some sort of data, maybe I should move this a little bit off to the side. I don't think I have a lot of room here. So if I wanted to do an insert, so void insert, that took some sort of generic type T and it inserted data, then one way I could think about it is it would insert the data into the body. So let's just say body.insert, which is not a real pointer we have, but I guess it's the idea that we're trying to capture here. And then in that case, it really will just insert it into this list, right? So let me actually move this down. So another way of phrasing that might be, rather than say insert it into the body of the list, we're inserting it where the head pointer is the next of this pointer, right? So if I was to apply this to a node, then I could say that the if I said head.insert, let's just say is the current node, then if I said insert, actually I guess the next one is next. If I took the next pointer and used that to insert, then it will insert it to the list to the right of this thing. Right, so the idea here was, and I didn't put the head, but we'll have to write that code outside of it. If that I start at the head and tell it to insert, and it goes to the next one and inserts it into the next list, then it will be this list over here, which again is a linked list, so I can insert things into it. Right, so this would be what we've been talking about with the recursion. So this is the what's the word? The reduction operation. And it's a reduction operation because it makes, I can't fit it on screen, it makes the list smaller. And so I don't have to explicitly put like a -1 or a division or something like we talked about with the other cases. I'm still doing some sort of reduction in size here, right? Just by chopping off the head and only looking at the next part of the list, I'm reducing the size of this linked list in a way. So it's still a reduction operator, so it will work with our recursion. So that's one of the two parts of recursion that we need. Does anybody remember what the other part is that we're missing here? So what's the other part of a recursive function that we're going to need in order to make this work? And again, it's okay if you don't remember the technical name, but stopping point, right? So we're going to need some sort of stopping point. Right, so if we look at this, what might be our stopping point? So at what point should we stop following the pointer and inserting? And there's a couple different answers, but if you can come up with one. The node on the right side, okay, fair point. So if we reach the far right of the list, then we know that we're done at stopping point. You're right. Is there a way we can check that? You stop when size reaches a point. Also fair. Right. So if size was 1, we could say that, right? And again, we could do that if we did a different implementation where we maybe kept track of the size somehow. But I guess here we don't. So you're both right. Yeah. And then check for null. So that's what we're actually able to do with the data we have. These two that you guys said are also correct, but we just don't have a way to keep track of them as far as our actual program goes. But yeah, if we check for null, then we know we're good. So what we can do here is we can say if next is null, then we do the actual insertion. So we say next is equal to a new node. So let's just say node that will construct based off the data. So we'll just say it holds the data and makes a new node. Right. So this was our stopping point, or the actual term for it is base case. And so now we have a way that seems to do it recursively. So we have both a base case and a reduction operator, and we have a recursive call here, so it calls insert itself. Now the thing here is that we need this to actually operate on a node rather than a linked list in order for this to work. So I think let's try to code this really quick and just see if it works, and then we'll come back and do the other ones. So let's expand this node class. Yeah, let's just reuse this one. So we'll say functions for recursion. And then what we'll do is we'll say void insert t new data. Oops. And that will insert the new thing. And then in advance, let's maybe just write the deletion and lookup, and then the print. Right, so that should be fine. I think that's all okay. We can, I guess, change this delete at to return a t as well, but I think this is okay. Alright, so let's go down here then, really quick, and try to write this. So in order to write the node classes, actually let me put this here so it's easier to read. So we'll just say, maybe I should put it above this. Right, so we'll take these and we'll throw them down here at the bottom. And then to quantify it, right, I need to put, since it's a template class, I need to put template class t above each of the functions, and then I need to specify that this is coming from the node of type t is the one I'm writing it for. Okay, so let me just do this. This one returns a t, so we'll need to change that really quick. I accidentally copied that. Right, okay. And then we'll just say return t here so that the compiler doesn't get angry at me. Alright, so let's try to actually translate this here. So we have insert the data. So if the next is null, that was our base case. And because this is a node class function right here, then I have direct access to next. So I could say something like this next as well if I really wanted to. But let's just maybe leave it at next. So if the next pointer is null, if we're at the end, we want to do the actual insert. So in that case, all we need to do is we need to set the next equal to a new node, so a new node pointer, and we're going to put it the data that we got into it. And then that would be it, and then we'll just say else. Then we need to recurse. Right, so we said insert, and then we'll insert into the next node. So what I'll need to do is I'll need to call insert for the next node, and then I will insert the data into it. Cool. So that seems to work. Maybe, hopefully. Let's write print really quick, just so that we have it. So really that's just going to be essentially the same, right? It's going to be if next is not null, then we'll keep going. So here we'll just say if the next pointer is not null, then print the next node. And then before we do that, actually this might be a good thing to consider. So let me print the data right here. And then maybe at the end we'll print a cout and line. Right. So what would happen if I was to move this line to the bottom? Would it still work? Or still print in the correct order? I just want you to think about that a little bit. And we'll try it in a second, but let's actually write the list here. So recursive linked list. Normally I would write a class for this, but maybe we'll just be kind of lazy about it. No, I suppose we shouldn't be. So let's go down here really quick. Let's write the recursive one. So I'm just gonna copy and paste all this, and we'll just change it a little bit. So let's name this rec linked list. And then we'll write the thing there for it. So it'll have a pointer to the head, and then we're just going to insert based off of that instead. So when we go and we do insert, we will, oops. We'll say if the head is equal to null, then yeah, we'll have to immediately call that. So if the head is null, we still do have a specific case where we're going to have to insert it at the beginning. So I'm going to have to say that the head is equal to a new node pointer, which has the data. Otherwise, what we were saying is that we could just recursively do it. So we'll need to call the head. So we'll say head insert new data. So if we don't have a head, we need to make one, but if we do have a head, we'll just insert it into the head and it will follow all the way down. Now I guess I do need to at least kind of write some of this. We'll just leave this blank for now. I think this is alright. We'll leave this blank. I'll just return head sub lookup at index. That way we have it for later. And then here we'll do a print, so we'll say head, oops, print. So this recursive version of a linked list that I should actually write the thing here for, recursive linked list, recursive linked list, recursive linked list. That should all be good. Really, all it does is it just uses the head as a starting point, or as a starting point, and then calls the head version of the function. Okay, so that should at least let us compile now. So let's say I go and I want to make a second linked list here. And let's just say this one takes floats, and we'll call this maybe R list for recursive linked list. So we'll make a recursive version of it, and then let's just insert 4.0, and then we'll maybe add 2 more things here. So we'll say 2, and then we'll say maybe 8.4. And then let's try to print it. And we'll see that it should hopefully work. Node use of class template requires template argument list. Because node is also, it's a template class, so I need to specify a type for it. Node class template cannot be constructed. Well, okay, maybe this will work now. We'll find out. Okay, that seemed to work. So it runs, and we have all this input up here, which is from what I wrote before. And then we have here, so it wrote 4 to 8.4, which was the, this is main, which was the contents of our list. So it seems to work. It seems to insert something at the end every time, so our recursion seems to be fine. And then it printed it in the right order, right? Okay. So what would happen, so my other question was, if we go back to that print that we had, so that was way up here. So if I had here where I was printing, so what I did is I said if the next pointer is not null, if there's a pointer that we can follow, then go and print it. Then what would happen if I move this down here? Would it still print correctly? Or would it print kind of randomly? Or is there some sort of pattern that would happen if I print it this way? So I guess my hint is look at the order of the calls, because what's different now if I throw this at the end versus if I throw it at the beginning is that this code is now before, and then this code is now afterwards. So if this code is going to print the rest of the list, what do you think is going to happen maybe? So let's maybe take a look then. So if I print it, you'll notice that we have 8.424, which was the reverse of this list. So 8.4 was supposed to be the last one, and then 2 was the middle, and then 4 was the beginning. So if I move the print to the end, it actually prints it in reverse. And the reason that is, so this was that head recursion versus tail recursion stuff, is that I do the function call at the head here now, and the actual code at the tail, whereas before I was doing the code at the head, i.e. first, and then the recursive call at the tail here. So if I change the order that I execute things in, I'm going to get that it actually executes backwards, which may or may not be a good thing depending on what you're trying to do. Well, just something to consider for the future, I suppose. Right, so that seems to cover the insertion recursively. Let's maybe do just one of these. The deletion is maybe a little bit more challenging. Yeah, I think I need some extra stuff here. Let's try to work that one out, and then I guess I'll leave the lookup one alone, and then I want to talk about one other thing, and if we have time, we'll come back to the lookup. Right, so let's say I'm going to do a deletion, so a recursive deletion. And again, all I have access to is the head. Now, something to consider is if I have a scenario where I need to delete the head again, then I guess I do need to replace the head. So we'll need to address that fact. We'll still need to consider, if we're deleting the head, we're actually going to have to look at that in the class body, the linked list. We can't do it with recursion. Which is okay because we don't have anything to recurse on anyways, so that's fair enough. But if we wanted to delete another thing, then we know we can kind of traverse it, so I could maybe, if I wanted to delete something, I can delete it on, again, like a smaller list. And so I can call delete, but what I'm going to need to do is, if I call an index, then we know this is 0, 1, and 2, but in the context of this smaller list here, then this one would be 0 and that one would be 1, right? If I consider this other part here to be a smaller linked list. So what I'll need to do, I think, is call it with the index minus 1 to account for the fact that we're removing something at the beginning, since we are kind of using it as a counting variable. And that would be our reduction again in this case. Now, the problem there is the actual code once we get to the deletion part. So let's at least start with our recursion. So we have, we'll just say void, and we'll say delete at. Index, I guess it's an int. So what we were saying is our actual recursion part would be that we will take the next and we will delete at it, which seems to check out. That is the recursion part. We're just calling the same function. And like we said for the last one, we're calling it on the next node in the list, which would be a list of size 1 less to the right of this. So what I can do here is I can say index minus 1, and that should take care of that. Right, so this was our actual recursion part, and then this, again, that's our reduction operator because it's making the thing smaller. Actually, I guess the whole thing would be our reduction operator. Both of these are reducing it in some way. So one is making the list smaller, than the other is making the count of that list smaller. So this is the reduction operations. I guess we have 2. So we need some sort of base case here, and then we need the actual code to go along with it. Right, so in this case, I think what would make sense for a base case is once the index is 0, then we know that we've reached the correct thing, right? Because this index here is counting how many more further we have to go. So if I was to call this with delete 2, then it will enter at the head as 2. It will get subtracted by 1 and be 1 here, and then by the time it gets here, it will be 0, right? So if we keep subtracting by 1, then it will eventually reach 0 when we're done. Now there's a bit of a problem, I'd say, with that. So if I ended up getting my pointer here and it's 0, the index that is, so the index is 0. then I might have a bit of an issue because I no longer have a pointer to this thing beforehand. And so if I do the deletion, I'll be able to delete this node, but I'm going to have a bit of an issue because I don't think you can really delete this. That doesn't make sense. So the thing that we're currently pointing to is this, right? This keyword. I don't think we were allowed to do that anyways. But on top of that, I no longer have a pointer to the last thing because it was the last call in that recursive call order, so the recursive call stack. What I'm maybe going to have to do is stop one early then, and then use that to work here. Because if I stop one early and stop on this node, then I do have access to the next node, which is the actual one that I want to delete, and then I can access the one after it too. Right, so what we'll have to do is we'll have to stop one early. I'm gonna move all this. Yeah, we'll keep that in there. So we'll need to stop one early. Right, so if the index 0 is the current object that we need to actually do deletion, then the one before it would be when the index is 1. So I think here a better base case would be if the index is 1. That lagged pretty badly. Alright, there we go. If the index is 1, then we want to do the deletion. Right, so what that would say is that we need to delete the next object, but before we do that, we should actually probably redirect this pointer to go around it. Right, or in this case, make it the end of the list. So we have to be careful in the way we do that. So we'll need to set the current objects next to the next one, and then we'll need to delete it afterwards. Let's see, so I kind of want to move this downwards, but I don't know how well this program supports that. Add to current page. Am I allowed to move this down? We'll say that's good enough. Let's make a little bit more space here. Right, so the order I need to do it in is I need to, kind of like we've been doing with the normal delete, is I need to make this pointer redirect around this object and then cut it off. So what I need to do is I need to set the next is equal to the next thing in the list, which is the thing that we're deleting, that next. Which probably looks gross to read right now, but it should be correct. And then we need to delete the next one now. So we'll delete the next node. Right, so what this says here is that we will take this pointer, redirect it around it, and make it equal to this one's pointer, so it'll point to whatever's next, in this case null, and then we'll delete this one. Right. So what's my problem with this? There is a problem. It's just I haven't run it yet, but I do know there's a problem. Is there anything that you notice might be an issue with these two lines? And specifically, I'll give you a hint. It's this one. That one is not right. What's wrong with it? So consider the order I did it in. I set next equal to be the pointer afterwards, which is what I want. But now this pointer is gone, right? I've overwritten it by doing this. Which means when I go to delete the next, this is pointing to the thing after it. And then I accidentally just deleted the thing that's ahead of where I want to delete rather than the thing I'm deleting right now. And if I flip the order, then I am kind of still at a loss because I'm going to delete it before I get to actually use it. So in the in the case of recursive deletion, what I'm going to have to do is keep a temporary pointer in order to delete it. So what I'll do is I will keep a node pointer called, let's just say temp, and we'll set it equal to the current next, so that way we can delete it later. And then we'll set our next equal to the one that we said, which was 2 ahead, which was the next, the next, and then we want to delete the temporary pointer, which was still pointing to the old one, which was the next one. And then now, that should be okay. I already have a brace there. All right. Now that should actually keep a reference to this temp one while I modify my current next. That way I can actually delete it for real. So let's try to program that really quick, and then we'll just talk about maybe one more thing along with this. So what we said was if the index was 1, so if the next node is the one that needs deleted, then we need to delete it. So what we said was we'll make a temporary node pointer, temp, and we'll set it to the current next, and then we'll overwrite our next to be equal to 2 forward, right, and then we delete the old node. I guess it's not old, let's just say delete the node. And then otherwise, if we're not at the end of the list, or one from the end of the list, then what we need to do is we need to delete using the list that's to the right of this, and again we said that we need to reduce the size by 1. And I think that's all we said, right? That should be everything. Oh, that's not the move tool. Yeah, there we go. So that appears to be everything. I guess just for the sake of consistency, let me say this is the base case, right? Is when the index is 1. And we could do this with a index of 0, but we'd have to do an extra thing where we keep track of what the previous node is, which might be a little bit annoying, so let's not do that. Okay, so that should take care of that. Let's go here and test it. So we'll say rlist.delete at 1, which should delete the number 2, and then we'll just see if it actually works. And it definitely does not seem to. So we still get 2 here. Oh, it's because I didn't write the recursive linked list version of it. Right, so I wrote the node version, but we have the recursive linked list actually, there's like an entry point, right? It calls the node. So delete at, yeah, we have nothing here, so no wonder it's doing nothing. What we need to do is if the head is null, then we will just return. So that's not something I addressed, but if the list is empty, we shouldn't delete anything from it. So if the list is empty, do nothing. Else, if the index is 0, then we're deleting the head. Right, so I'll need to do something here where actually I guess I need to do the similar thing here. So I need to say node t pointer temp is equal to head, and then we set the head equal to the head next of the head, which is the one to the right of it, and then that becomes the new head, and then we delete the old head. Now I don't think I did this in the original delete, and I should have, so let me go back and replace that. Delete at, well, perhaps that works as is. Oh no, I kept a separate variable. Never mind, we're okay in the original. I did that alright. Right, but anyways, this was like the normal deletion code that we had for our node, but we just have to do it to the head because we can't recurse if we're deleting the head. And then else we need to delete using the head as a starting point. So we'll say delete at index. Okay, so let's try calling that again. We'll see if it works. And there we go, it does actually delete 2 now. So that's good. Cool. So now we have recursive ways to do this. And we can do pretty much anything recursively. So we could write almost any algorithm we've done recursively. This is just, I guess, an example of how we could do it with a linked list. And again, I maybe hint doing this for assignment 9 because you know, there's a chance that you might have to do this in that. Not with a linked list, but with something similar. Okay. Any questions on that? And if not, I'll move on to maybe a practical application of a linked list. And I say practical, but it's maybe not that great in reality. Okay, so let's consider a scenario where we have a linked list. Doesn't matter if it's recursive or not. It just works, and it has the insertion, deletion, and lookup. And I guess what we care about is maybe the print and the insertion only here. So I'm going to create a linked list. And we'll just call it list. And then I'm going to feed it some numbers. So let's just say I feed it list dot, maybe I should make this all in the same color. List dot insert. We'll say it takes integers, I guess, here. 5 list dot insert 9, and then we'll say list dot insert 4. And maybe some practical application I can do with a list is I can use it to sort these things while it's inserting. Right? So let's try to sort this way. So if we look at the execution of this, let's insert 5, then 9, then 4. So on the first level, that's going to be a head pointer, which is null. So it's just going to be this. So it seems like when we insert the first thing, we just need to insert it as normal and create a new node. Put it in 5, put the data into it, set its pointer to be null, and then we redirect the head to actually point to it. So that'd be insertion of 5. That one is normal, how we expect it to be. And the next one's going to be normal as well. So if I go to insert 9, then what I'm going to do is I'm going to create that node called 9. I'm going to set its pointer to be null, and then I'm going to traverse the list until I hit the end, which is right here, and then redirect this pointer to point to this. So nothing new so far. Now, let's say we want to insert 4. Let's actually make this, let's make it something between 5 and 9, which is, let's just say 6, and then we'll do maybe 4 afterwards. So if I wanted to have this list sorted, then the 6 needs to go here, right? Right, so what I want to do is I want to traverse as normal. So I'll start here, and then I'll maybe work my way down. Perhaps it would make more sense if I had more numbers here. Let's throw in 2 lines here. So let me reorder this a little bit. Let's say this one will say is 3, and then I'll insert a 4 right here. And then I'll make a linked list. I just want to make it a little bit longer for the sake of the example. Right, so now instead, we would insert 4, 5, and 9, which are already in order, so it's just going to insert them like normal. So I end up with something that looks like this, right, where we have 3 things. The last one is null. This would be 9, 5, and 4, and then I have the head pointer right there. Okay, so hopefully that's pretty straightforward. If I insert 4, 5, and 9, then I'm just going to get that list. Now, if I go to insert 6, its place in the sorted list would be right there, right? Between 5 and 9, because that's where 6 goes. So what I need to do is I would need to insert and go here, and then go to the next one. And then once I go to the next one, we realize that that's too far. So I should maybe stop before I do that and insert it into this position instead, right after the 5. So the first thing is, how do I check for that? It seems like the insertion works kind of normally if we want to put it into the list. But how do I know to put it somewhere now versus before? So before I was strictly just checking for null. What do I have to do extra now if I want to sort it? Maybe what I should do is, so if I go here, we know that 6 goes after 4, right? So what I can do is maybe check that 6 against the 4, see, does it go before it? Or does it go after it? And if so, go forward. And then here we go to the next one and say, does it go after that 5? In which case, yes it does, so we keep going here. And then once we hit that 9, we realize that, oh, the 9 is bigger, so we need to insert it somewhere in between. Now again, we might need some sort of previous pointer, and maybe it would help if we took a look at the next one similar to the way we did before, where we maybe just take a peek at the one in advance. So what I'm suggesting here is if we wanted to do insert that sorts, and we did pretty much everything the same way. We're just going to traverse the list. So we'll keep some sort of node pointer. And we'll call that current, and as per usual, we'll set it equal to the head at first. And what we'll do is we'll say while current next does not equal null. So while we're not at the end, then we'll just do some stuff. So we'll go down here. I guess I do need a little bit more. And the part of our while loop here is we just said that we went to advance the next node. So current was equal to the next one. So this just moves it along, right, is what we did. So this looks exactly the same as our other insert that we had earlier. I'm leaving a space because we're going to need to do something extra. And then what we said was if we get to the end of the list, then we can just insert it like normal, right? So I can go here and say if... Actually, I don't need an if. If it passes this while loop, we know it's at the end of the list, which is how we inserted previously. We didn't do any stopping early. So we would just say that the current, which is the last one in the list, its next is equal to a new node whose pointer will be null and who will initialize with the data. So it's equal to a new node. I should say new because it is a pointer. New node that will make out of the data that we had. Right, so this is exactly the same code so far. Basically just say go to the end, and once we get to the end, throw the data at there using a new node that contains that data. Now what we need to do is we need to consider when we actually insert the head. Oh yeah, so I guess I probably needed to check for that too. So if the thing was null, I needed to actually insert the head. Let's just pretend I did that. So we'll just say if head null. Then put at head. Right, so I have two other things I need to consider that we'll just try to quickly get through. So the one is if I've reached the position which is not at the end, so let's just say for the 6 that was here, put that there, then what I need to do is I need to stop early, I need to stop traversing the list, I shouldn't go to the end anymore, I should just insert right where we need to go. And then I should just stop and not actually do anything else. So perhaps what we should do is we should look ahead to the next element in the list, and if that next element is bigger than the one we're about to insert, we should stop. So what I propose here, let me move this up so that we have a little bit more room, is if the next pointer if its data, so the thing that it actually holds, is greater than the current thing that we're inserting, which is the new data that we're wanting to put in, then we know we've reached a stopping point. So what we should do is we should insert the new thing. So what we're going to have to do there is if I wanted to insert this 6, what I'm going to have to do is create the new node. Right, so I'm going to create a new node as per usual, set it equal to 6, set this pointer equal to null. Let's remove this red stuff here, maybe just to make it easier to read. So what we're saying is we need to create a node with the 6 in it, and then what I need to do is I need to redirect this 5 to point to here, and then this to point to there. So I need to account for both of those. So if it's greater than, what I'm going to need to do is create a new node and then set its pointer and the pointer of the current one. So what I'll do is I will move all of this down because I think we're going to run out of room. add to, nope, that was the wrong thing. Click. I think it moved it all the way up here. Here we go. So let me move that down a little bit. Let's just erase this. Okay, so we have a lot more room to work with now. So what we said is we want to set it equal to the new node that we're creating. So let's create it first. So we'll make a new node pointer. And we'll call it new node. And we will set it equal to a new node pointer. That we'll put the data into. So we'll create a new node from the data. And then what we'll do is we'll take it, and we need to set this pointer equal to it, and then we need to set its pointer equal to the next thing in the list. So I think the order here matters a little bit. What I'm going to do first is set the pointer of this equal to the next of the current node. So current next. So we'll set it to equal this side, and then we'll set this equal to here. And the reason I do that rather than do it the other way around is if I go to set this based off of that pointer, then it will have been deleted and it will just point to itself, and then we just get a cycle, which is not what we want. So what I should do is set this first and then do the other one next. So what I'll need to do is set the current node's next pointer equal to the new node that we just created. And now it should be inserted. Okay. I think I'm missing one thing here. I'm missing I'm missing a curly brace. Okay. And I don't think we'll code that because I don't think we have time. But this should now insert it into its sorted position. So two things I'll leave you with. One, we need to account for one extra thing here, which I won't go into too much detail about, and I'll let you think about. But if we need to replace the head, then we need to account for that, right? Because then we don't have a pointer to like redirect around. So what you might want to do first here is check if the new data is less than the head, then do something special, which would be just basically the same code all over again, just accounting for the head. And then the other last thing I'll leave you with is the fact that we have a new way to sort. So you don't have to use bubble sort or selection sort. You can sort with a linked list. And this isn't a great way to sort. There are way better ways that aren't, I would say, even as hard as this. But it kind of sorts as it goes. And in reality, if we were to do some sort of mathematical evaluation, this is not really any better than bubble sort or selection sort. It's in the same time complexity is the word for it. In terms of like how many steps it actually needs to do, it's going to be roughly the same as bubble sort and selection sort, but it's it might actually do better in some cases. So this here, if we know a lot of the items are kind of like in reverse maybe, then we won't really have to traverse a lot of the list when inserting. So the problem here is that if everything is sorted, this takes a really long time, because then I'm just inserting everything at the end of the list if it just goes in order, right? Like with the 4, 5, and 9, I just inserted them like normal. But if I know it's kind of like in reverse almost, then I know I'll kind of insert things at the beginning, and then the end just kind of trails off to the end, in which case we would get something that's better than bubble sort or selection sort. So this has its uses. In general, you might be able to make it better than bubble sort, but it kind of depends on how your data is formatted. But it is an alternative. It is there. There's a way better, or two way better sorting algorithms that you'll learn about in 302, or that we might talk about if we have extra time here. So who knows? But I guess that's that. So if you have any questions, as per usual, I'll stick around for a few minutes. Assignment 7 is due on Wednesday now, and I think that's about all I have to say. So I'll stick around for a few moments, but if not, I guess I will see you all on Wednesday.